Somewhere on the coast where you live, there is a line. It is the line the sea reaches today, on an ordinary day, at an ordinary tide. Hold that line in your mind, because it is going to move, and it is going to move further than almost anyone expects. There is enough ice sitting on Greenland and Antarctica right now to raise the global sea by about 65 meters. Nobody serious is saying all of it will go, but here is the part that should stop you. We may have already locked in several meters of that rise, and there is no button we can press to take it back. The reason hides inside one quiet misunderstanding. When we picture an ice sheet in a warming world, we picture it melting, softening at the edges like an ice cube in a warm drink, shrinking smoothly, giving us plenty of warning. That is not how it works. A great ice sheet does not gently melt away. It holds, and it holds, and it holds, and then at some hidden threshold it collapses. To understand why, we have to do something strange. We have to stop thinking of ice as a solid, and start thinking of it as a slow, colossal fluid with a breaking point built in. Start with the thing itself, because most of us have never really looked at it. An ice sheet is not a frozen lake. It is a dome of ice the size of a continent, on average around 2 kilometers thick, and in places nearly 5 kilometers deep. There are only 2 left on Earth, and they are wildly unequal. One sits on Greenland, holding enough ice for about 7 meters of sea level. The other buries almost the whole of Antarctica, and it is a giant beside it, holding more than 50 meters of sea level all on its own. And even Antarctica is really 2 ice sheets in a trench coat. East Antarctica is the ancient, enormous, mostly stable half, sitting high on rock above the sea. West Antarctica is the smaller, lower, wetter, far more nervous half, much of it resting on a bed that lies below sea level. Keep that split in mind, because almost all of the danger we are about to describe lies in the West. Under its own staggering weight, that ice does not just sit there frozen in place. It flows. Slowly, like extremely stiff honey, it spreads outward from the high, cold interior toward the distant coast. Snow falls in the middle, packs down over centuries into dense ice, and that ice creeps outward and downhill, squeezing into fast, narrow rivers of ice that we call outlet glaciers. When those glaciers reach the ocean, some of their ice breaks off as icebergs, and some keeps going and lifts off the seabed to float, spreading into flat platforms on the water called ice shelves. So picture the whole machine, a thick, slow dome in the center, fast glaciers draining it at the edges, floating shelves where the ice meets the sea. Every part of that machine is about to matter. Now, a fair question. These places are among the most remote and hostile on the planet. How could we possibly know what a mile of ice is doing at the bottom of Antarctica? The honest answer is that for most of history we could not, and the ice hid its secrets. What changed is that we learned to watch it from space. A pair of satellites called Grace did something that still sounds like magic. They flew in formation and measured tiny changes in Earth's gravity as they passed over the poles, and from that they could literally weigh the ice and watch it getting lighter year by year. Other satellites fire radar and lasers at the surface to measure its height to the centimeter, so we can see the ice thinning. Aircraft trail radar that sees straight through the ice to map the hidden landscape of rock beneath it. So when scientists say an ice sheet is losing hundreds of billions of tons a year, that is not a guess. It is a measurement, taken from orbit, of a continent quietly losing weight. And the measurements tell us something we cannot ignore. The loss is not steady, it is accelerating. Both Greenland and Antarctica are shedding ice several times faster today than they were just 30 years ago, when these satellites first began to watch. This is the crucial context for everything that follows. We are not describing a stable system that might one day be nudged. We are describing a system that has already started to move and is picking up speed. For most of the last several thousand years, this machine was close to balanced. Think of it as a bank account, but the currency is ice. Snowfall in the interior is the deposit. Ice flowing out to the sea and breaking off as icebergs is the withdrawal. When the deposits and the withdrawals roughly match, the ice sheet holds its size, and the sea stays where it is. And here is the idea that changes everything. An ice sheet does not have to melt in place to raise the sea. It can raise the sea just by flowing off the land and into the ocean faster than new snow can replace it. The ice that ends up in the water raises sea level whether it got there by melting or by sliding. So the entire question of sea level turns out to be, underneath, a question about flow. What controls how fast the ice slides off the continent? Speed that up even a little, sustain it for a century, and the ocean rises. And that is exactly where the feedbacks live. Go back to those floating ice shelves, the platforms where the glaciers spill out onto the sea. For a long time they looked like a footnote. They are already floating, so when a shelf melts, it does not raise sea level at all, any more than a melting ice cube makes your glass overflow. But the shelves are secretly doing one of the most important jobs in the whole system. They are wedged against the coastline and snagged on underwater high points, and they press back against the glaciers, feeding them from behind. They act like a cork jammed in a bottle, holding the fast ice in. Now pull the cork. Take that shelf away, and the glacier behind it is suddenly unbuttressed, free to flow. It can speed up dramatically, in some cases doubling or tripling its pace, pouring ice that was resting on land out into the sea. So the floating ice that raises nothing when it melts is the very thing holding back the grounded ice that raises everything. Lose the shelf and you unleash the glacier behind it. Here is the next surprise, and it overturns how most people imagine polar melting. The dangerous melting is not mainly happening on top, in the sunshine. It is happening underneath, in the dark. Around much of Antarctica, a layer of relatively warm, salty water sits down at depth in the surrounding ocean, and shifting winds and currents can push it up onto the continental shelf and in beneath the floating ice. It reaches the ice at the crucial place where the glacier finally lifts off the bedrock and begins to float, a boundary called the grounding line. There, the warm water melts the ice from below, thinning the shelf and carving back at the grounding line, forcing it to retreat inland. So the real trigger is not warm air, it is ocean heat, delivered quietly to the underside of the ice, hundreds of meters below a surface that can still look frozen solid and calm. And the place it does its damage, the grounding line, is about to become the most important line in this entire story. Now watch what happens to that grounding line as it retreats, because this is where the ice quietly reveals its breaking point. Across large parts of West Antarctica, the land under the ice is not a gentle upward ramp toward the coast. It is a deep bowl. The bedrock actually lies below sea level, and it slopes downward as you go inland, getting deeper and deeper. That shape is a trap. When the grounding line retreats back down that reverse slope into deeper water, the ice sitting at the new grounding line is thicker, simply because the bed there is lower, and thicker ice at the grounding line flows faster. Faster flow drags down more ice, which drives the grounding line back even further, into even deeper water, where the ice is thicker still and flows faster still. Every step makes the next step easier. That is a feedback loop with no natural break, and it has a name: marine ice sheet instability. Past a certain point, you no longer need to keep warming anything. The retreat runs away on its own, downhill, and it does not stop until it finally reaches high ground that may be hundreds of kilometers inland. This is not a fringe idea. It falls out of the basic physics of how ice flows across a bed, worked out decades ago. And it is the single most important reason that West Antarctica, sitting in its deep reverse-sloping bowl, is considered the most vulnerable large body of ice on the planet. The instability is not waiting to be invented. It is built into the shape of the ground. There may be a second way for this to go, faster and nastier, and it is the one that keeps some scientists awake at night. When a floating ice shelf shatters and clears away entirely, it can leave behind a bare cliff of ice at the front of the glacier, standing straight up out of the water with nothing to lean on. Ice is strong, but it is not infinitely strong. Above roughly 100 meters of exposed height, an ice cliff simply cannot support its own weight. It fractures and crashes down into the sea. And here is the vicious twist. When that cliff calves away, the ice standing behind it is often even taller, because remember, the bed keeps getting deeper inland. So the freshly exposed cliff is higher than the one that just fell, and even less stable. Collapse exposes a taller cliff, which collapses, which exposes a taller cliff, a chain reaction of failing ice fronts. This is marine ice cliff instability, and if it turns out to be real at full scale, it could drain parts of Antarctica in centuries rather than millennia. It is also, and this matters, still genuinely uncertain, and we will come back to that honestly. Greenland plays a different game, and it matters, because Greenland is the ice sheet losing mass fastest right now. Here, surface melt is the star of the show. In summer, the top of the ice sheet warms above freezing, and vast sheets of meltwater form, pooling into brilliant blue lakes and rivers that run off or plunge down into the ice through shafts called moulins. The scale can be hard to picture. In an extreme summer, Melt can spread across almost the entire surface of Greenland at once, and the ice sheet can shed hundreds of billions of tons of water in a single season, enough by itself to lift the whole global ocean by a noticeable fraction of a millimeter in a few months. Two feedbacks make this accelerate. The first is about color. Fresh snow is bright white and bounces most sunlight straight back to space. But as it melts, it exposes older, darker ice, dust, and dark microbial growth, and darker ice soaks up far more heat and melts faster still. The second is subtler and more dangerous. As the surface melts down, the entire ice sheet gets lower, and lower means warmer, because you have descended into thicker, milder air near sea level. Warmer means more melt, which lowers the surface further. So Greenland can, in principle, melt itself downward past a point of no return, where even if the climate stopped warming, the ice sheet keeps shrinking because it has lowered its own head into air that is simply too warm for it to survive. If you want to know exactly where to point at one glacier in West Antarctica named Thwaites. It is enormous, roughly the size of Britain or the state of Florida, and it drains a vast basin of ice piled up behind it. Thwaites sits right on top of every danger we have described. Its bed slopes downhill inland into a deep basin, so it is perfectly primed for marine ice sheet instability. Its floating ice shelf is being melted from beneath by that warm, deep water, and it is cracking apart along huge fractures. Its grounding line has been retreating for decades. Thwaites on its own holds enough ice to raise global sea level by about half a meter, but its real importance is as a plug. By jamming the exit, it holds back neighboring ice that could eventually add several meters more. That is why you sometimes hear it called the most important glacier in the world, and why an international team of scientists is out on its surface and under its shelf right now, drilling and diving, trying to work out how close the plug is to giving way. If all of this sounds like a frightening story we are inventing about the future, the rocks have news for you. It has happened before, more than once. The Earth's orbit wobbles on long, predictable cycles, and those wobbles have repeatedly nudged the planet in and out of ice ages. During the last warm period between ice ages, around 125,000 years ago, the planet was only slightly warmer than today, yet global sea level stood something like 6 to 9 meters higher than it does now. The only place that much water could have come from is the ice sheets. Parts of Greenland and West Antarctica must have collapsed under a climate barely warmer than the one we are building today, and the rocks even hint at how fast it can go. In the meltwater pulses that ended the last ice age, the geological record shows periods where sea level rose by several meters in the space of a century, rates that would be catastrophic if they happened to the coastlines we have built today. Go back further, to warmer worlds still, and the coastlines were unrecognizable. The lesson written in ancient beaches and seabed mud is blunt. These ice sheets are not permanent fixtures. They are the current temporary answer to a particular climate, and that answer can change. Now we arrive at the property that makes ice sheets so treacherous to reason about: the delay. Ice this vast is slow. When you push it, it does not respond this year or this decade. It responds over centuries, sometimes millennia, groaning toward a new shape long after the push began. That means the sea level we measure today is not a clean reaction to today's warming. It is partly a delayed echo of warming from decades and centuries ago, still working its way through the system. And it cuts the other way too, which is the frightening part. The warming we have already caused has set changes in motion that have not fully arrived yet. We could halt every emission tomorrow, and the grounding lines that have already begun to retreat would keep on retreating, because the trigger has already been pulled. This is what scientists mean by commitment: a feedback that amplifies, a threshold that has been crossed, and a delay of centuries before the full result appears at the coast. Feedback, threshold, delay. We can commit ourselves to a future coastline long before we ever get to see it. So how much, and how fast? Here we have to slow down and be careful and honest, because this is where the science is genuinely hard. For this century, the mainstream projections put global sea level rise at very roughly half a meter to a meter, depending mostly on how much more we warm the planet. That alone is enough to redraw coastlines and force millions of people to move. But the numbers carry a long, heavy tail. If the ice cliff instability turns out to be real and quick, the plausible high end for this century climbs well past a meter, and the figures for the centuries after that reach several meters and keep going. And here is the uncomfortable truth at the center of climate science. The biggest single uncertainty in the whole field is not whether the planet is warming. That is settled. It is exactly how, and how fast, the great ice sheets will come apart. The mechanism is clear, the timing is not. And when the possible timing runs all the way from a few decades to a few thousand years, that uncertainty is not a comfort. It is the entire problem. It is also why you should be a little suspicious of any single confident number. The responsible projections do not give you one line. They give you a spreading fan of possibilities, narrow and manageable at the low end, alarming and open-ended at the high end, and the width of that fan is set almost entirely by the ice. Narrowing it is one of the great unfinished tasks of the science, and it is exactly why those teams are out on Thwaites in the cold and the dark. Here is a twist that almost nobody sees coming. When an ice sheet loses its ice, the sea right next to it does not rise, it falls. An ice sheet is so unimaginably massive that its own gravity pulls the surrounding ocean toward it, heaping seawater up in a bulge around its own coastline. Melt that ice, and you remove the pull. The water that was heaped up nearby relaxes and flows away, so local sea level right next to the vanished ice can actually drop, and all that water has to go somewhere. It redistributes across the whole planet and piles up on the far side. So if Antarctica sheds ice, the largest sea level rise shows up thousands of kilometers away, along coastlines in the northern hemisphere. The place that loses the ice is often spared the worst. The places that did the least to cause it can feel it the most. Sea level is not one number rising evenly in a global bathtub. It is a fingerprint, and every melting ice sheet presses a different one onto the map. It is easy to let a phrase like 1 meter of sea level rise slide past as an abstraction. It is not. Let us make it concrete. Most of the damage does not arrive as a wall of water on a calm day. It arrives as the new baseline underneath the storms. Raise the average level by half a meter, and a storm surge that used to be a rare, once-a-century flood now rides in on top of that higher sea and arrives every few years. The rare becomes routine. Higher seas also push salt water into the groundwater and up rivers, poisoning farmland and drinking water far inland, long before any street is permanently submerged. And the exposure is staggering. Something like 1/10 of the world's population lives within a few meters of sea level, in exactly the low, flat deltas and coastal cities that this water finds first. Think of the great river deltas, the Nile, the Ganges, the Mekong, home to tens of millions each, some of them sinking under their own weight even as the sea climbs to meet them. Think of entire island nations whose highest ground is only a few meters up. For them, this is not a distant forecast about the year 2200. It is the arithmetic of whether their country still exists. So when we talk about a grounding line retreating in the dark under Antarctica, we are also talking, with a delay of decades, about the line on your coast, and about hundreds of millions of people standing behind it. So what part of this can we still undo? It helps to sort the changes into 2 piles. In the first pile are the parts that still answer to what we do. Slower warming means slower melt, a thicker cork, grounding lines that hold their position. A great deal of the sea level rise this century is still genuinely up to us. In the second pile are the thresholds. Once a grounding line has retreated back past its ridge and marine ice sheet instability has taken the wheel, simply cooling back to today's temperature does not politely reverse it. Ice sheets have a memory. To grow one back, you cannot just stop the warming. You have to rebuild the entire dome, snowfall by snowfall, over many thousands of years, in a world colder than the one that melted it. So the picture is not hopeless, and it is not already fixed. It is a race. A race between how quickly we slow the warming and how many of these thresholds we quietly cross before we do. Step back from the ice and look at the shape of the thing we found. A slow, patient system, pushed gently, that hides its reaction for a very long time, and then amplifies it past a point of no return. Feedback, threshold, delay. Once you know that shape, you start to see it everywhere. It is the same shape as a body ignoring an illness until suddenly it cannot. The same shape as a quiet debt compounding in the dark. The same shape as a dry forest that looks perfectly fine right up until the spark. The ice on Greenland and Antarctica is not misbehaving. It is doing precisely what a slow system with feedback and memory does when you lean on it hard enough. It holds, and then it moves. The line on your coast is still there today. Whether it stays there is not, in the end, really a question about ice. It is a question about how well we understand the shape of slow things, and whether we choose to act while the holding still holds.